voltage regulator. So I invite engineer H.S. Jatana to kindly give his expertise over this case study on linear voltage regulators. Engineer Jatana, please.
Good morning, all of you. And today is the last day of this course. So we have taken up after a few sessions on VLSI design. So today we will discuss one case study where it will be clear how these concepts are being used in design of a circuit. So the case study is regarding a linear voltage regulator. So why it is known as a linear? Because earlier when these voltage regulators were made, they were made using BJT transistors, bipolar transistors, and bipolar transistors, they were used in the linear range of operation. So that is how the name came, the linear voltage regulator. So now, what is the requirement of voltage regulation? Last time in my talk, then I told that there are various voltage islands in a chip, in a single chip. There may be various transistors which need different power supplies. But from the outside, the chip gets only a single supply. If the chip needs 5 or 6 different power supplies, it is impractical to give from outside all these power supplies. So from the outside world, one power supply will come, and inside the chip you have to make voltage regulators which can take the outside power supply and generate various voltages. So this is a concept which is widely used. So today we will discuss about design of one such voltage regulator which we had designed and which we are using with memory SRAM, static RAM, because that memory, it needs two power supplies, 1.8 volt and 3.3 volts. But from the outside we are giving only 3.3 volt, and 1.8 volt power supply is being generated inside the chip. So now, what is a voltage regulator? So voltage regulator is a device, is a circuit that gives a constant voltage irrespective of the load. What load means, irrespective of the current drawn from that power supply, the voltage is fixed. It does not change whether you draw zero current or you draw a higher current, but the voltage which it is giving, it should not change with respect to the load. The voltage should not change with respect to the line voltage. So the line, there is some voltage which is being fed to this regulator. So if there is a change in that voltage, so that also the output voltage should not change. One very good examples of these voltage regulators which are commonly used in our houses are with the air conditioners. There is a voltage stabilizer. It is commonly known as a voltage stabilizer. It also does voltage regulation. So it takes the 220 volt supply and it gives the output 220 volt fixed. If there is on the input side, if there is a change, if the input supply goes to say 240 or 250, but the output is maintained at 220 volt only. So this is the concept of the voltage regulator. And another is, if that ambient temperature, if the temperature changes, the power supply should not change. So the power supply should be fixed irrespective of the temperature, irrespective of the load current, irrespective of the line voltage. So this is the condition of a voltage regulator. Now how this is achieved? So the output voltage, it is regulated by some internal circuitry. So and we have to design a circuit in such a manner so that the output is independent from the load current, from the line voltage, and from the temperature. So this is what the job is. We have to develop a circuit such that its output voltage is not dependent on temperature, it is not dependent on load current, it is not dependent on line voltage. This is what the job is. And these voltage regulators, they can be used as a single chip. You can see in the market many voltage regulators come which can give 1.8 volt, 1.2 volt, 3.3 volt, or this can be used as an embedded circuit also. In a bigger chip there can be various voltage regulators which are used as an embedded circuit. So this is the application. So as I told, it is mainly it is used as either as an independent chip or within the bigger circuit. So the whatever the case study, this pertains to linear voltage regulator. So first thing is we have to define the specifications and we have to define the features of this. So this voltage regulator, it should give 1.8 volt output. This is 1.8 volt output. 150 milliampere is a full load current. This means it should be able to give 150 milliampere full load. It cannot give more than 150. So the output voltage should be 1.8 volt, whether the current is 0 milliampere or maximum full load current is 150 milliampere. 350 milliampere is the limiting current. Limiting current in the sense, if you short the output of the voltage regulator and the current exceeds 350 milliampere, then the voltage regulator will shut down automatically. So it's a safety feature. If you short the output pad, so naturally huge current will flow and it will burn something. So to stop that, as soon as the current reaches 350 milliampere, that is the limit. So it shuts down. The circuit shuts down. There is a thermal protection also. That is 140 degree C, 140 degree J temperatures thermal protection. This means if the temperature of the chip, when the temperature of the chips become 140 degree centigrade, the voltage regulator shuts down, because beyond this there are chances of again burn up. So the voltage regulator has a temperature protection, thermal protection also, and again it restarts when the temperature drops to, there is a 20 degree hysteresis. So it will, if the temperature reaches 140, it shuts down, and then the temperature will start coming down, and when the temperature reaches 120 degree, again it starts. So that is the meaning of the hysteresis. So this linear voltage regulator is known as an LDO. LDO means low dropout. So what is the meaning? This low dropout, the meaning is its low dropout is to 95 millivolt at full load and 67 millivolt at no load. This means it takes some voltage which is the input and it gives some output. So from the input to output, the voltage drop, that is known as a dropout. Okay, so it should be at no load, it is 69 millivolt, and at full load it is 295 millivolt. So this is the specification. This circuit was made in 180 nanometer process, twin well process with single gate and single Vt. All transistors which are used in this, they are having single threshold voltage. It has 4 level metal. There are 4 level of metals, 4 metal process, and this we have made this circuit at SCL here in Chandigarh, and we have tested this also, and I will show you the results of this. So now before this we have to, when we take up design of any circuit, what we have to do, we have to study the specification. So what is the meaning of specification? So here voltage regulator also has certain specifications. They are, you can call it performance parameter. So we will discuss these performance parameters one by one. First is the load regulation. Now here it is given here load regulation. What is the meaning of load regulation? So load regulation means it refers to change in the output voltage with respect to change in output current. Like if there is no current, there is some output voltage, but if there is a change in the output current, if there is a change in voltage, so that voltage divided by the reference voltage. So this is how it is defined as. So here the formula is load regulation. It will be del Vref over Vref, and it is expressed as a percentage, so into 100. So this is the formula for this, and we can see this one. So this Vref is the change in regulator voltage, and regulated voltage at this Vref is the regulator voltage at typical conditions. So del Vref means the how much voltage has changed if you change the current from no load to full load. That is del Vref. This one, that is del Vref. So how much voltage has changed if you change the current from input from no load to full load. So that del Vref divided by Vref and into 100, this is the meaning of load regulation. Then there is a concept of, we talked that about temperature, the output voltage should be insensitive to temperature. If there is a change in temperature, the output voltage should not change. This is ideal, but it will somewhat drift. So that is why we have put a parameter here. So how do we measure? It is again very simple to do this, and this is the formula of the temperature drift. So this is Vmax minus, this is Vmax minus Vmin. So this Vmax, this is the voltage. Vmax is the voltage at maximum temperature. Vmin is the voltage at minimum temperature. Vmax minus Vmin. This is the change in voltage and divided by the change in temperature. Tmax minus Tmin. So this is the maximum regulator voltage over applied temperature range. This is the minimum temperature range, maximum temperature range. You take the difference of these two and divided by the V nominal is the nominal voltage. That is the voltage at typical condition at room temperature at 25 degrees centigrade. And you multiply it by 10 raised to the power 6. Here we are multiplying by 10 raised to the power 6 this one, so that this one. So by this you can express this in ppm, parts per million. So that is why 10 raised to the power 6. So temperature drift is expressed as, like, say if the spec is 50 ppm per degree centigrade, this means 50 divided by 10 raised to the power 6 into voltage. So this much change in voltage, and 10 raised to the power 6 is microvolt. So 50 microvolt it will change with respect to 1 degree C. With change in 1 degree temperature, output voltage will change by 50 microvolt. This is the meaning of this temperature drift. So this parameter is also important, and we have designed a circuit where this temperature drift is minimum. We will see what these values are, minimum values. Then there is a concept of line regulation. Now the line regulation is, this voltage regulator takes the line voltage from outside. If that voltage changes, so the output voltage should not change. So this is the meaning. So there is a supply voltage. If there is a change in the supply voltage, which is given by del V supply, which is this one, which is given by del V supply, and if there is a change in this, then you change in supply voltage. If there is a change in the supply voltage, then the output voltage will change. Okay, so this del V supply is change in supply voltage, del Vref is change in the output voltage. So you divide these two, divided by Vref into 100. This is expressed as a percentage. Wherever we are multiplying by 100, it is expressed as a percentage. Then another important parameter is ripple. Ripple, what is a ripple? You see, ripple rejection means in any DC supply, ideally it should be straight one. There should not be any change, but it is not possible. So there is some ripple. There is some sine wave on that. So the signal is like this. If I draw it here, it will be like a DC supply should be like this, straight line. Okay, but this is ideal. It is never like this. So the way it is like this. there will be some ripple on this, like this. There will be some ripple on this. I have different frequencies, so there will be some ripple like this. Okay, so this now we have to reject this ripple. If this ripple is more, for example, if I make it slightly like here, this is more ripple. If this ripple is more, then it may destroy, it may have some side effects, it may destroy the circuitry. So first, then we have to measure the ripple, and we have to specify, we have to put a limit that it cannot be more than this. So normally this ripple is ripple rejection is given in logs, 20 log dB in decibels. So how to measure the ripple? This ripple is V, the supply which is coming to the regulator. So that is V supply peak to peak. So there is some ripple there. So on this supply, this one, this V supply peak to peak, and then we have a this V reference is your output peak to peak change in regulator output voltage. That is the V reference. That is the V reference. This one. Okay, so we will see how much, if there is a change, if there is a ripple in the supply, how much that ripple is transferred to the output voltage. So you divide these two and you take 20 log. So it will come in decibel. So this is the ripple rejection. It will be in decibels, and we will like to this also to be minimum ripple should be minimum. Then there is a concept of load transients. Load transients means if there is a sudden change in the load, there will be some transients at the output. Okay, so those from, like if the load changes from no load to full load, you see in our houses what we see is if you suddenly put a device which takes lot of current, like if you switch on two air conditioner, you will see there is a dip in the output. You can see the dip in the supply, or that you can see if there is some bulb is glowing, you will see there is slight difference in the intensity of the light. By that you can make out. So whenever you change the load, there are certain transients for some time momentarily, and then it settles down. So these are known as load. If the load is changes, there are transients. So this also we have to observe what those transients are. Similarly, there is a concept of line transients. So whatever input voltage is being fed to this voltage regulator, if there is a change there also the output also, there will be some transients, but it will settle down after some time. Transients are momentarily, and after some time they will settle down to the fixed output voltage. So this also we have to observe what those transients are and how much time it takes to settle down. This also is a parameter. Then there is an output noise. There will be some noise over that output voltage. We can measure that noise, and this in the noise, there are noise means there are AC signals of different frequencies. So the bandwidth, it can have a very high bandwidth also. It's starting from 50 hertz signal. It can have 1 kilohertz and 10 kilohertz or 100 kilohertz. It will have all signals of all frequencies. So that is the noise part. That also we have to restrict. The noise should be minimum. There is a spec on that. We will show you here in the last slides. Then there is a concept of dropout voltage. Dropout voltage, again, as I explained earlier, this is the difference between the input line voltage and the output voltage. Low dropout means we want the difference should be minimum. It should be within 1% of its nominal value. Then there is a shutdown current. Shutdown current means this is the maximum current which the regulator can give. If the current exceeds this, it shuts down. That is how it is known as a shutdown current. So it is a maximum. It is 350 milliampere in our case. So if the current exceeds 350 milliampere, like if you short the output of the regulator, so naturally if you short some output voltage source, it will take lot of current will flow. But as soon as the current reaches 350 milliampere, voltage regulator can give 350 milliampere, but it will not give more than 350 milliampere when the current reaches 350 milliampere, it shuts down. So that is the shutdown current. Similarly, there is a spec of peak current. One, there is a concept of average current, then peak current. Average current is 150 milliampere. So there is a maximum output current which the regulator settles to shut down current limit. So there is a concept of peak current also. So this also we will see all these currents. Then there is shutdown temperature. Shutdown temperature means the temperature at which the chip, if the temperature of the chip increases, then the chip should shut down automatically. So in our case, we decided that the shutdown temperature should be 140 degrees centigrade. If the temperature inside the chip increases to more than 140, the chips automatically shuts down, and it will automatically restart when the temperature drops to 120 degree, or you can set the limit, or the temperature drops to 100 degrees centigrade. So this means there is a temperature sensor also. You have to then design a temperature sensor, because you have to measure the temperature in the chip. Then only you can decide whether to shut down or not. So there is a temperature sensor also in this. Regulator bias current. What is this bias current means? The total current which is absorbed, which is consumed by the voltage regulator, that is known as a bias current. It is drawn from the power supply, and this is the total current. Then there is a concept of power efficiency. Efficiency, it is the ratio of output power, like power input, power output. Power output by power input into 100%, that is the efficiency. How much power you are giving and how much power is being outputted. So that is efficiency. You divide both these, that is the efficiency. These, so many are the parameters of this regulator, this circuit. Now, this is the architecture. I don't know if it is visible to you clearly or not, but I will explain the various blocks of this. First block, this one, if you are seeing, this block is a band gap reference. What is the meaning of a band gap reference? This means this block, it generates a voltage of 1.1, close to 1 volt, 1.1 volt. This generates a voltage close to 1.1 volt, which is fixed voltage. Band gap voltage means it does not change with respect to temperature or anything, with respect to changes in load current, output current. It is always fixed. So, and this voltage is fed to all other circuit. Because then the voltage becomes stable. So this is the source of that voltage generation. How it is done, we will see in the next. Then once you have generated a fixed voltage, then it is fed to an amplifier. There is a first stage of amplifier here also, but here this is the second stage of the amplifier here, second amplifier. Then this is output stage, the third stage, which will give you the output. This is the output voltage pad. This is the output voltage, and this is the last stage. This is known as the output buffer amplifier also, or the third stage of the amplifier. So this is the output. This is the load. And output, this is the ground pin, and output to ground, you have to put a capacitor. This is a capacitor which is being put. This is the load, and there is a circuit. This is for overcurrent protection, because in the output stage there is a heavy transistor. There is a power transistor to regulate that transistor, and there is a overcurrent protection circuit. So as soon as the current in this block increases more than 350 milliampere, this circuit will shut down this transistor. And then there is a over temperature protection here. So there is a temperature sensor which is sitting on the chip. It keeps on measuring the temperature. As the temperature increases more than 140, so it shuts down the chip. The chip is shut down, so the temperature will settle. So these are the various blocks, and this is the circuit after designing, after layout. So this is how it will look like. And if these are the pads, these 1, 2, 3, this pinkish color you are seeing, these are the pads. Like here to here, these are the pads. This is the chip, and wire bonding will be done at the outside device at these pads. Now, in the previous slide, like this is the band gap, this is second stage, this is the output stage, this is overcurrent protection, this is temperature protection. So we will see how these blocks are in this layout. This is the band gap. This portion is the band gap, and this is the second stage of the amplifier. This is the second stage. This is the third stage. This is a output buffer, or it is known as a power mouse, because this actually the power mouse is here. This small strip you are seeing from here to here. So this is a transistor actually. There are around 180 fingers, and this is metal. This is metal. This green, this grid and this grid. So this is connected to output voltage here. This is ground. 1, 2, 3, 4, 5, 6. These pads are ground. 6 pads. These 6 pads are output. Okay, so because the current is more, 150 milliampere it has to take. So that is how you can see lot of metal is used. That from here to here, this is 1.6 millimeter, and here to here it is 2.43 millimeter. So this is a dimension. This is 2.4 millimeter. This is 1.6 millimeter. This is the size of the chip, and these you are seeing here. These things there. These are the various resistors and capacitors which are used in this circuit. So mainly the controlled path. Now this is the over temperature and over current protection circuit sits here. Over current and over temperature product, all circuits sits here. So I cannot show you the blow up of this because of the limited screen size. And this is the power transistors, and this is a complete chip which after layout it looks like this. So just again I will explain with the reference to this block. These are the various blocks. This is first block is a band gap reference. The objective of the band gap reference is to generate 1.1 volt fixed volt, which is not dependent on any temperature. And then once we generate 1 volt, we feed to the amplifier, to the second stage of the amplifier, and then it is taken to the output stage of the third stage of the amplifier, which is a output buffer. I will show you what the circuit is in the subsequent slides. Then there is a overprotection circuit and overcurrent protection. So the same thing is coming here. This is the band gap. This one, band gap uses BJT transistor also. BJT and all other transistors are NMOS. So this is the band gap. This is the second stage, and this is the third last transistor, which is known as the power MOS. This one, this small, you are seeing light greenish in color. This one patch of this thing. This is a transistor. These are the metal lines. This one, this is metal. This is a pad. Actually, this is a pad, and here this also is metal. There are 4 metals in this, so you are seeing only the top metals. There are 4 metal lines, and metal 4 and metal 3 are interconnected also. So here these are the output stage, and 6 pads are used. 6 because there is more current. It has to draw a lot of current. That is why the more number of pads are used. So this is a complete chip. Dimension is 1.6 millimeter into 2.4 millimeter. Now we have seen the various blocks. Let us see the circuit of each block. So this is a band gap reference. What is the principle of a band gap reference? Band gap reference, I told you, first we have to generate one voltage which is independent of temperature. So how do we do this? This is a BJT. I hope you are able to see this. So in a BJT, this is emitter, this is collector, this is base. So this voltage is VBE. So there is a VDD here, and you bias this transistor by this current source. So at this point, this is base to emitter voltage. So as you know, the base to emitter voltage, okay, it falls with temperature. VBE, base to emitter voltage, it falls with respect to temperature, and this is a reverse junction, reverse biased PN junction. As you this transistor is an NPN, so this junction is reverse biased, this junction is forward biased when this transistor is on. So this VBE with respect to temperature it falls, and how much it falls? It falls by minus 1.5 millivolt per degree centigrade. So for every 1 degree centigrade change in temperature, the voltage V base to emitter, which is known as VBE, falls by 1.6 1.5 milliwatt, 1.5 millivolt. So there is a fall of 1.5 millivolt, which is explained written by here. Okay, so if this line, the voltage at this line, it is falling at the rate of minus 1.5 millivolt per degree centigrade. Now I have to make another line here. I have to make a VT generator. VT threshold voltage you have heard of, which is KT by Q. So we make a, again this I will show you in the next slide. How do we make? Again we are using this BJT transistor to make a this VT threshold voltage. This VT is a thermal voltage, so VT generator. So now this thermal voltage is KT by Q. So this means it increases with temperature. KT. So K is that Boltzmann constant, T is temperature in Kelvin. Okay, so this is K. So it increases with temperature here. So if I make a this VT generator, which is a thermal voltage generator, its voltage, this output, it is increasing by 0.087 millivolt per degree centigrade. 0.087 millivolt per degree centigrade, it increases. This falls by minus 1.5 millivolt, this increases by 0.08. So this means if you make this also minus plus 1.5, so this falls by minus 1.5, this increases by plus 1.5, so both will cancel out. Okay, so this means you multiply this by K. So this is what this vector is, K. You multiply by this K, you take this output. Now this slope of here, this signal, and slope of this signal is same. Now you feed this to a op-amp, operational amplifier, or you add it. Basically you add it, it becomes 0. So 0 means it is not dependent on the temperature. Okay, so this concept is should be clear from now. So this is an amplifier here, and this output is taken here, and then this output is fed back to a power MOS to give more current. Here the voltage is stabilized now with respect to temperature. It is not changing with respect to temperature. How we have seen this? Because we are using VBE, which is it falls with temperature, and we are using a thermal generator, VT generator, whose voltage increases with temperature. Slope is different, but we adjust the slope of this by multiplying with K, and then you do the summing of these two, and then this is the output voltage, which is not dependent on temperature. So this is the way we have generated this voltage. So this is the complete circuit, band gap reference circuit. Now this is what earlier it was shown NPN, NPN. Here it is PNP transistor is used. This is the transistor here, and this is a NMOS used. It is a current source. You have to bias this transistor, so some current is being fed from here like this, and this is the base. This is emitter, right? So this is base to emitter is this VBE. So this is being fed. This is amplifier op-amp. So this is ground. You can see here, this is ground. So emitter to base VEB is fed here, which is decreases with temperature. This, and here this voltage, this is the current source. Again there is a PNP transistor which is of different size as compared to this, and to generate that KT by K term, so a resistance is used, and at this output the KT by K, that the thermal generation will come, which has a positive slope. Okay, so here VBE is not used here. So this, because we are taking the voltage from here across this resistance. So the value of this resistance is adjusted so that the slope at this point becomes same. Only thing is here it is decreasing, here it is increasing, and we are adding these two, and then it is being fed to another stage. Output is taken from here. This is a kind of a buffer. It is a common, you can see here, it is a source follower which you have studied kind of thing. So this output follows this. Okay, so this, and it's acted as a buffer only, and this circuit is for trimming, so that you can fine trim these values and adjust this voltage. So finally you get a BG out here, band gap reference. So band gap reference output voltage is coming here. This voltage is not sensitive to temperature. So this is how this is created. And then next, these are the results. So, initial accuracy was 0.44 percentage, 0.4 percentage, maximum 0.5%. It should not, it should be less than 0.5%. And temperature coefficient is 26 ppm per degree centigrade, 26 parts per million. Okay, so from this is the temperature range minus 40 degree to 125 degree. So this means it will change 26 microvolt per 1 degree centigrade. This is the meaning, it will change only. So ppm parts per million, and this is a line regulation. 0.06% is the minimum, maximum is 0.6. So it should be less than 0.6% line regulation. Ripple rejection is 61 decibels dB. So we are getting 61 decibels. 61 decibel mean 20 log. So this means 1000 times you are able to reduce the ripple. If in the input signal there is some ripple, but in the output it will appear, it will be divided by 1000 times, and that signal will come at the output. Okay, because if in the input signal, if say it's a ripple is 1 millivolt, but the output it will be 1 millivolt divided by 1000, which becomes 1 microvolt. So 1 microvolt ripple will be there. So we have divided this by 1000, and the bandwidth is 100 hertz, in the 100 hertz. So this is how 1000 times is 60 dB, 20 log 1000. Log 1000 is 3, so multiplied by 20, so it becomes 61 dB. So these are the results which are measured actually. Now come to the second stage. Okay, so this is the second stage of the amplifier. You see, I hope you have studied these op-amp architectures. If not, just I will explain here. This is the differential stage. This is one transistor, positive terminal in, this is another transistor in, and as you know, it needs a current source here. This is the current source P transistor. This is the active load of this. This is the active load of this, and output is taken at this. So this output is taken at this, and it is fed here. So this is the second stage. There are two transistors here. We take the output here, and another to this. This is a load. This is the biasing of this transistor. So output is taken here, fed to here. Now you have to bias this NMOS. So we are using this PMOS to bias this. It acts as a current source, and to a current source, current mirroring is used from here. So this is acts as a current source. This is a PMOS. It generates a fixed current, and this current is mirrored here also, because this also acts as a low current source. So the sizes of these three are adjusted depending on the requirement of current. The current requirement here is different than here. So sizes of these transistors are adjusted in such a manner. But you can see this is the gate. So it is going to gate. This is the gate. It is going to gate. So you can see this VGS. S is this here. The G to S, G to S, G to S is same of all these three transistors. So this way it is adjusted here. So you take the output from here, and this is second stage. This is the output stage. You take the output and this is a buffer. You can see this, it is a PMOS and NMOS output is it's taken here. This is known as a push pull. In the books you might have studied this a push pull amplifier, so these will act as a push pull. Here one transistor is shown, but actually there are finger in this output as I and this particular thing, this which I am showing, these two MT9 and MT8, if you see our this block is MT9 and MT8, this block, these transistors, there are around 180 transistors, 183 transistors. Okay, so because the current is more, so here it is being shown as single transistor, this one. So there are many fingers of this, and this particular stage, second stage, this is a differential stage, this is the second stage, this is here. There are few transistors, not a big circuitry, you can see it is here only. This is output stage, this is output stage, this is the metals only, this is metal lines. They are connected to here, it's a PMOS, they are connected to source and drain here, source here. This is the circuit, and this is the output. Now these are the results which we have got. So of this these are the simulated results of second stage amplifier. The open loop gain is 83 decibel, 83 dB, maximum is 103, minimum is 83, and unity gain bandwidth is 4.5 megahertz, phase margin 77 degree, and gain margin is typical 17.7 dB. So these are the results of second stage amplifier. Now these are the simulated waveforms. Now you can see the results here. The first is a load regulation. This means this is the output voltage, this is the current. So the output voltage, now here this you will not be able to, because this is in millivolt kind of thing, you will not be able to see much, but you can see this output voltage stabilizes, it doesn't change. If once there is a change in this, this is the initially some current is used here, and finally this current, this is the current which passes through that capacitor, because there is a capacitor at the output, so that needs to be charged, so some current it takes, and once this voltage is established, is becomes stable, this also becomes minimum, and finally it will go to 0. This is the temperature coefficient. This is the here the temperature is plotted. I will read out here, it is this minus 40 degree, this point is 60 degree, this is 60 degree, this point is 125 degree. So it is plotted from minus 40 degree to 120 degree. This, now this line, this one, this is with no load, this is no load curve, and from here to here you can see when it is minus 40 degree, this is, as the temperature increases, the voltage is also increasing till some temperature which is 50 and 60 degree, till this temperature, this is 54 or 55, and after that it starts falling. And on here the difference, this is 1.7, this point is 1.798, and this point is 1.805, so it is around a few millivolt kind of thing. If you, these values, this is in millivolts only, though it appears to be, it is a blown up thing, that is why it appears. So here it is 1.79 millivolt, and this point is 1.81 millivolt kind, so the difference is less than 100 millivolt. So this much change is occurring with respect to in this entire temperature range. In this is with low load, and if there is a load, naturally some voltage will fall here. So you can see this curve is with load, so the output has fallen to some, it has fallen to some value. So this is the temperature coefficient. Now this is the power supply rejection. Now here in this is plotted the frequency, like I will tell you, it is starting with hertz. So this is around 100 hertz, this is 100k, Okay, so it's a logarithmic curve. It's a this is log. So this means this it starts with 1, 10, 100, 1 kilohertz, 10 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz, like this. So it is a logarithmic here. And on this side, this also is a log, so it is a dB, 20 log, because ripple is measured in dB. So this also is a dB. So this is the output voltage. So it is 60 dB which we told. So no load. This is no load. The output voltage remains same at 60 dB. The ripple rejection is at 60 dB here till this point. This point is close to 1000 hertz. So at 1000 hertz, the ripple rejection is very good. 60 dB. 60 dB means 1000 times it is reject. It is dividing the ripple by 1000 times. Then it starts falling. You can see here. Oh, sorry. Then it starts falling here. So this means the noise which is more than 1000 hertz, the division is becoming less and less. So here this point is 20 dB. This point is 20 dB. 20 dB means 20 log. So 1. It is dividing by 1 only. Okay, so this means whatever ripple of this frequency, which is more than 10 kilohertz, if there is a ripple of more than 10 kilohertz present in the line, so that will be divided by 1 means same. The same ripple will appear at the output at high frequency. Okay, so here, but less than 1000 hertz, it is 60 dB. It will be divided by 1000 times. So this is how it is. And this is no load and this is full load. Full load, it is slightly less. This much is, it is 56 or 55 dBs. So it is slightly less, and this is how it looks like. And if it increases more than 1 megahertz, then again it improves, starts improving like this. So this is the power supply rejection which we got. Next is the line switching. You see, if you switch the line, this is the, here from the input no voltage is coming. You can see it is 0. At this point, input has started coming. So we have switched the input line. You have switched the input line from here to here. This point, it goes, then it stays here. This is the output voltage. So at output voltage, nothing will come. And as once you have switched, it will start rising. You can see this, it start rising, and then it becomes stable after some time. So it takes this much time, this much. From here, it becomes stable. Okay, so this is the band gap reference circuit, because from the input no supply is coming. At this point supply comes, so there is no band gap voltage. Here the supply comes, here immediately the band gap reference is stabilized here. This is the transient. So at this point it is stabilized and it is fed to the op amp, second stage and final stage, and that is how it is taking time to build up. So it is built up and here it is settled. And this time is in, if you see, the time is plotted. So here this point is 6 millisecond and this is 6.0, this is 6.45. So this is 6.0 millisecond, this is 6.45 millisecond. So 0.45 millisecond in the whole, this output voltage is stabilized. So this is the line switching again. So earlier we discussed 0 to 1, now it is 1. If the line is there, and immediately it is shut down. So here the output voltage is coming. So as soon as the input is shut down, so this also shut down immediately. So you can see this. So it shut down immediately. This is the line switching from on to off to on, both. And this is the load switching. If there is a load, you are switching the load. So here no load is there, and finally we are switching the load. So there will be a transient and then it stabilizes. So it is less load here and then more load here. So this is the output. So it takes time to stabilize when you switch the load. So these are known as transient. This is a steady state. And again, this is again another load switching. So from here to here, this load is switched from this point to this point, and you can see how this output is varying. Now there are two parameters which we have to discuss. We have discussed all this. There are only 2-3 more slides. One is overcurrent protection and over temperature protection. I told earlier that there is overcurrent protection also. Overcurrent protection in the sense the purpose of overcurrent protection is to limit the output current. Okay, through this delivered by the regulator. So it will prevent excessive currents in power MOS transistor, because if there is some problem in if the some output is shorted by mistake, so heavy current will flow. The chip should not burn. The chip should automatically be shut down. Okay, and because now the question is, what happens if more current flows? There is a term known as electromigration. Electromigration means, because metal lines are made of aluminum, so if more current flows, what happens is some of those aluminum atoms, they are taken off. Okay, so there is a heavy rush of current, so some of the aluminum atoms, they are taken, and so there is a void in that. Okay, so there is a crack in that metal track, and once there is a track in that, so the current density, because then the width of the metal decreases, so more current density in the remaining portion increases. So when the current density increases, it generates more heat. Okay, and so more aluminum atoms are taken from that track. So that is how the wear and tear, it's a slow wear and tear, it happens, and finally there will be some voids, there will be cracks in the metal, and finally our metal, it will become open or it will become short. Okay, so this happens at when the current is more, and it happens at the temperature. If you increase the temperature, that then also it happens. So for this, the overcurrent protection is there. So this is the simulation for a overcurrent. This is the simulation for a short circuit protection. Okay, so this is the current which is being consumed. So you can see this is the output voltage here, and if the current reaches, this is 350 milliampere, the current reaches here, this is 350, if as soon as it reaches 350 milliampere, it is coming down, so current is the circuit is being switched off, so the current starts decreasing, so this is going down. Then there is a thermal overload protection. So it is if the temperature inside the chip increases to some higher value, then also the circuit is shut down. So there is most thermal shutdown requires built-in hysteresis. Now there is here in our case, if the temperature temperature of the chip is at 140 degree, the chip shutdowns. But the question is when it should become on, it automatically shut down. So for the chip to become on again, so the temperature has to fall to a certain minimum value. So that is 20 degree or 30 degree less. So 140 degree it shuts down. It turns on at say 100 degree. Okay, so there is an hysteresis so that the circuit should not oscillate. If that hysteresis is less, then the circuit may oscillate. So to avoid this, that hysteresis is kept in that. So this is the over temperature protection. It is in the form of a thermal shutdown mechanism which can sense the chip temperature and automatically shuts off. Okay, so the bipolar BJT VBE drop is used as a temperature sensing element. So temperature sensor, how to sense a temperature? You use BJT as VBE drop, because VBE of any PN junction, it is, as I told you, it is proportional to temperature. For VBE will drop 1.5 volt with every change of 1 degree centigrade. So if you can measure the VBE, you can measure the temperature. So in all this, even in the voltmeters or multimeters which measures the temperature, they measure the VBE. So voltage, and then they map onto temperature. So this is how we have also used BJT circuit, and we are measuring the VBE voltage, and then finally mapping it to temperature. So this is how it is, the over temperature protection. So here you can see it is coming down here. This is coming down here, and there are 2-3 colors which may not come clear, yellow and green. So it shows because when the chip shut down and when the chip takes over. This is also overcurrent and temperature protection together. This is the output, and this is how it will appear, these thermal cycling phenomena. This it will look like this on CRO, on if you take the picture on a CRO. So now, as I told, this chip was used with a memory chip, because the memory wanted memory required two voltages, 3.3 and 1.8. From the outside only 3.3 volt is given, 1.8 volt is generated by this chip, and it is supplying to the memory. And these are the results of, integrated testing using LVR and SRAM. Now I will explain what it means. You see, in a memory, this signal is a WEB, write enable signal. Okay, so write enable is when you are writing in the memory, then you need some. So this is the write enable signal, and this one is the V out, violet color. This is the I out. This is the V out, which is 1.8 volt of voltage generator output. This is the current. The current is always between 120 and 140. 120 and 140. Why it's changing? Because this enable signal is changing. This is okay. This is enable signal of the memory, and the frequency here. The frequency here is 1 megahertz. It's written 1 megahertz. So this frequency is 1 megahertz. So you can see the output, and this is the current. Here the frequency is 38 megahertz. So you can see this is this signal only. At 38 megahertz it will look like this, because it doesn't have much time to settle for this here. So it will almost become a triangular wave at 38 megahertz. You can see this. So at 38 megahertz you see this output voltage. It also starts, there is more variation. This is current. So see this, there is a more variation in the current. Okay, so all these, how much these variation, how much hysteresis is there, all these parameters are written here. Though it is very small, you will not be able to read, but in the PPT you can see these things. So this is actual, when this data, when a load is put, of the memory load is put. So when we use this with the memory, so these are the simulation results. This is again, you will not be able to see this data. I will read out the various parameters. So here the load regulation is 1.4%. Temperature drift is 200 ppm per degree centigrade. We have measured line regulation is 0.19%. Output impedance is 200 milliohms. Power supply rejection, we are getting around 40 to 60 dBs. Dropout voltage is 108 at no load, and at 108 millivolt and 400 millivolt at full load. The output noise is 500 microvolt RMS. Output noise is measured as RMS voltage, so microvolt, 540 microvolt. Short circuit current is 460 milliampere. Peak current is 1 ampere, 1.28 ampere. Shutdown temperature is 140. Hysteresis is 20 degree. Quiescent current is 7 milliampere. Power dissipation is 1423 milliwatt, means 1.4 watt. So it consumes 1.4 watt of power. So all these results are here, given here, and this is what the complete design of linear voltage regulator. If you have any questions, you can please ask, and if you want, you can give your feedback also at this. This is the email which is given here. You can also send me your feedback about all, and if you have any questions for the last 2-3 sessions also, you are most welcome to ask. Yes, you can carry on one by one. You can please, if there is any question, you can ask participants from different colleges who are connected.
Hello. Hello.
Yes,
So this
please.
is Shilpa from RMS CET Bareilly. So I just want to know that those results that you have shown, that HSPI simulations. Hello.
Yeah, I'm.
Hello.
Yeah, carry on. Yeah.
So
Yes,
you
I'm.
are able. Yes, sir. Sir, those results that you have obtained, we can vary the technology also in those results when we would be fabricating. Like in P-Spice, there is no such option for changing the technology. But in H-Spice, is it possible to change the technology that we are working on?
You see those technology parameters, na, if you are using a piecewise, there are certain values of there are certain transistor models are given, one model, okay. But it depends on the foundry where the device will be fabricated. They have different set of parameters. So those you should have. Then and one is the spice parameter, H spice or P spice. We are using H spice. So the circuit you can simulate by using a H spice. You will get some value. Then you fabricate the chip. Okay, you fabricate the chip and you measure the actual results on the chip. Okay, there will be some difference. So sometimes there will be some difference. Now your question is on piecewise. You should have the model parameters. The model parameters you will get from the companies. They have the exact model parameters. Otherwise, in piecewise, those parameters are not exact.
So, like if for the research purpose, if we want to just change the technology and we want to observe that how it is changing with the technology that we are working on. So, is it possible
Then
in
for
some
each
software that we can?
then for each technology, you should get the model parameters for each
So
technology.
we can import those parameters also if they are not available.
No, you have to ask for these parameters. You have to, like, there is a cadence or synopsis. These are the EDA companies. You have to take tools, proper tools, then they will give you.
So
Otherwise, the
these
tool,
files can be imported in the PSpice library or those
no,
device family.
eSpice is there are certain EDA tools which are available free on the internet. There is only one technology parameter will be there, one model will be there. But if you want two,
Okay.
three like 90 nanometer, 100 nanometer, 130 nanometer parameters model,
So that I
they will not be available free, na? No one will give you those things. So what you either you
okay.
purchase a tool from some EDA company, you purchase the tool. He might give you for one technology only. He will not give you for all. Okay, so these model parameters are not given. Only thing is to the companies who are into designing of these things, they have to the companies who are fabricating these chips. Those they will give only to those people who design circuits. No, otherwise they will not give. So it is
Okay, so
not
then these results would vary practically, no? So that we would obtain by simulation.
simulations. Whatever for you in the college, whatever model parameter the piecewise will be having for one technology, no, either 90 or I don't know
Yes, sir.
which one is there. You work on that. You understand the concept. Your
Okay,
objective should be to understand the concept only. For that is
okay,
good
okay.
enough. For that is good enough. You should understand how the circuit is designed, how the circuit works, these concepts, what are the design concepts. You should try to learn those concepts. That is important for you in a college.
Okay.
For that is good enough. Piecewise is good enough.
So one more question is there.
Actually,
Sir,
this
आप
is not
introduce
a
करो.
question, but just a comment. Okay,
Yeah,
the temperature specification minus 40 degree to 125 degree C is for military purpose.
yeah,
It seems this chip was designed for military purpose.
true, true. Yeah, we all our because since I am working with ISRO, so we all our circuits are designed for military or space grade. So for this is the temperature range.
Okay,
Like,
thank you so much, sir.
yeah. Any other question from any other college? No one has any questions? Then we can close. So So okay, then if no one is asking, so then we can close this. Thank you very much for being connected for this whole program. And I think the next program already Professor Rajesh has informed you. It will start